Hello students, welcome to the next video. Now we are going to discuss an important topic, that is moving coil galvanometer. Moving coil galvanometer is a device which is used to detect the current in a circuit. So it basically serves two purposes in the electric circuit. Second, when the direction of the current in the circuit is unknown to us, then we first connect galvanometer in the circuit, which not only help us to detect the direction of the flow of the current in the circuit, but can also give us an approximate magnitude of the current flowing in the circuit. The working principle of this moving coil galvanometer is that when a coil carrying current is placed inside a uniform magnetic field, then it experiences a torque, the magnitude of which depends directly on the amount of the current flowing through the coil. So if we are able to calculate the torque experienced by the coil, then the amount of the torque experienced is directly proportional to the magnitude of the current flowing through it. Construction. As you can see on the figure, it consists of a scale, a pointer. Here we have a two pole pieces, concave pole pieces of the bar magnet. Especially concave pole pieces are used over here, not the flat, because they produces an important type of magnetic field which we call as the radial magnetic field. Here we have a soft iron cylindrical core around which a copper winding is done. One end of the copper winding will be provided a positive connection from the circuit and another will be connected with the negative connection. The coil is connected with the hair springs. The function of the hair spring is to bring back the coil not only to its original position after switching off the circuit, but also they help us to keep a limit on the amount of the deflection produced inside the coil, which is very important for the measurement of the current in the circuit. What is a radial magnetic field? We already know that the torque acting on the coil is given by tau is equal to NIAB into sine theta. So if this coil rotates in the pole pieces of the bar magnet, in the pole pieces of the concave pole pieces of the magnet, then due to rotation, if the angle, this angle theta between the current and the direction of the magnetic field changes, then the torque acting on the coil, it will also undergo a change. So if bar magnets used are having a flat ends, in that case, then the torque acting on the coil, it will be directly proportional to I into sine theta. That is, not only it will depend upon the value of the current, but also depend upon the angle between the direction of the current and the direction of magnetic field. Due to which, as the angle theta will change, magnitude of the torque will change and we will not be able to detect or measure correct value of electric current. So it is important to make this torque independent of this angle between the current direction and the magnetic field direction. For this purpose, what we do, we make use of the concave pole pieces of the magnet, which produces a magnetic field which is called radial magnetic field. As you can see in this figure, this is the external circumference of the iron cylinder, and these are the copper windings present on the iron cylinder, and the blue lines are indicating the direction of the magnetic field lines. As you can see that any magnetic field line which is originating from the north end and it is moving towards the south pole of the magnet, it is actually passing through the exact center of the circular cylinder, iron cylinder, like this. This means that here you can say that every magnetic field line which is moving from north to the south pole is actually directed along the radius of the iron cylinder. We call this type of magnetic field as the radial magnetic field, the important point here is that whatever is the position of the coil in the concave pole pieces of the magnet, there will be few magnetic field lines present in this arrangement such that the direction of the current and the direction of the magnetic field will always be perpendicular to each other. Here theta is the angle between the normal to the plane of the coil and the direction of magnetic field. So this type of magnetic field is used. In this case, whatever is the orientation of the coil inside the concave pole pieces, the value of the angle theta will always remain 90 degree, or we can say that plane of the coil always remains parallel to the magnetic field, due to which sin theta will always be equal to +1, due to which the torque acting on the coil, it will always be proportional to only one factor, that is the current flowing through the coil. So in this case, radial magnetic field help us to detect as well as measure correct value of the electric current passing through the circuit with great accuracy. Next, theory and working. Here we have again the same figure which we have used for finding the torque acting on the coil. The current I is flowing in the clockwise direction. The sides of the loop are of length B and A, and angle between the normal to the plane of loop and direction of magnetic field is theta. We know that the torque which is acting on the coil is given by the equation tau is equal to NI AB. Theta over here is equal to 90 degree. So under this torque, the coil will tend to rotate about its axis. This is the axis of the coil about which the deflection of the coil in the anti-clockwise direction will take place. So as the coil will deflect, it will turn through a small angle. Let that angle we take it as alpha. Let that angle of deflection is alpha. So this torque which deflects the coil through a small angle alpha in the concave pole pieces, we call this as the deflecting torque. So this torque is actually known as the deflecting torque. Now as this coil rotates, these hair springs connected with the coil, they also rotate along with it, due to which their stretching takes place, and due to the elasticity of the material of the hair spring, a restoring torque is developed in these hair springs. So that restoring torque will also be directly proportional to the amount of the angle by which coil is turning. So that restoring torque tau r for restoring will be directly proportional to alpha, or we can write down that restoring torque is equal to K into alpha, where K is our torsional constant of the material of the spring, which is nothing but the restoring torque produced per unit twist. So whenever 1 unit twist is produced, what will be the restoring torque developed inside the spring material? That will give be the value of the torsion constant. Now in the beginning, when the coil will be passed a current I, immediate a torque NIAB, deflecting torque act on the coil, which will slowly turn the coil from initial position to the final position by an angle alpha. As the coil will turn more and more, the restoring torque will go on increasing, such that in the equilibrium position, when the restoring torque at angle alpha becomes equal to the deflecting torque, in that case the coil will stop rotating. As the coil will stop rotating, the pointer attached to it will also stop rotating. So the pointer will give us a amount of the current passing through the coil, which we can note down with the help of the calibrated scale on which the pointer will be moving. So in this case, when the equilibrium position is reached, the restoring torque K alpha, it will be equal to NIA into B, or we can write down alpha is equal to NBA over K into I. Now all these bracketed factors, number of turns of coil, strength of the magnetic field, area of the coil, and the torsion constant of the material of spring, they are constant. Their value Once fixed cannot be changed. So this is a constant. So this indicates that alpha is directly proportional to I. That means any deflection produced in the coil is directly proportional to the current flowing through it. Also, from the same equation, K alpha is equal to NIAB, we can write down this equation as I is equal to K over NBA into alpha, which can be written as G into alpha, where G is equal to K over NBA, and it is known as the galvanometer constant, or it is also called the current reduction factor for a given galvanometer. So once a galvanometer is constructed, materials in the galvanometer constructions, they are fixed, so we cannot change the hairspring. K is fixed, number of turns of the coil are also fixed, strength of the magnetic field due to the concave pole pieces cannot be changed, and area cannot be changed. So this is a constant factor, we call it as current reduction factor or the galvanometer constant. Next is the figure of merit. This is an important physical quantity related with the galvanometer. It is defined as the current which produces a deflection of one scale division on the galvanometer. So on the scale of the galvanometer, divisions are marked like this: center 0 division, 1 division, second division, 1 division, second division on the left and the right side. So if a pointer is moved on the scale by passing current through the galvanometer, initially it will be pointing towards the 0 value. So how much current should we pass through it so that it suffers deflection towards either side equal to 1 unit, so that it moves from 0 division to first division. Amount of current required for producing this much deflection, we call it as the figure of merit. So figure of merit is actually represented by G, which is equal to I over alpha, which is again nothing but K over NB over A. Next is sensitivity. Sensitivity means how much small or the smallest amount of current can be detected by a galvanometer. A galvanometer which is able to detect even smallest amount of the currents is said to be more sensitive. For this, the galvanometer's pointer must show a large scale deflection even for a very small amount of the current that is passed through it, or a small potential difference applied across its ends. So if it is able to produce even large scale deflection even for the smallest of the currents, that type of galvanometer will be highly sensitive. Two sensitivities are defined for the galvanometer. One is the current sensitivity. It is the deflection produced in the galvanometer when unit current is flowing through it. It is the deflection produced in the galvanometer when a unit current flowing through it, and it is represented as IS, I for current, S for sensitivity, which is equal to alpha over I, which will be equal to NBA over K. So you can say that if I is equal to 1, so if you keep I is equal to 1 unit, then IS will be equal to alpha. So you can say that see that current sensitivity is inversely proportional to current. So highly sensitive galvanometer will have high value of IS only when current in the coil it will be small. Next is the voltage sensitivity. It is a deflection produced when the unit potential difference is applied across its end. This voltage sensitivity is represented by IV, or you can also represent it with Vs, voltage sensitivity, which will be deflection produced per unit applied voltage. Using Ohm's law, V is equal to IR, it will be equal to NBA over K into R. Okay, or you can also write down this expression as that voltage sensitivity is actually current sensitivity divided by the ohmic resistance of the galvanometer coil. So how can you increase the sensitivity of a galvanometer? Four factors are there which affect the sensitivity of galvanometer. First is the number of turns present in the coil. So by increasing number of turns, we can increase the torque on the coil. This means that even for a small amount of current, due to greater number of turns, it will produce enough torque to show a large scale deflection. But we can also not go on arbitrarily increase the number of turns, because if number of turns are increased, that means we are making use of longer wire around the iron cylinder. So if a longer wire is used, then its resistance will also increase. So when resistance will increase, instead of increasing its sensitivity, it will decrease the sensitivity. Second, increasing the magnetic field. This can be done by using powerful concave pole pieces magnet. Third factor is by increasing the area of coil. We have also seen that torque also depends upon the coil area. So coil area can be increased in order to increase the sensitivity, but one thing we have to make sure that by when we increase the area, we are using greater size coil, it is going to make the apparatus size bulky. And one thing we have to keep sure that when area is increased for the coil, it must not go out of the magnetic field region between the concave pole pieces of the magnet. And last, by decreasing the torsional constant. You can see that current sensitivity as well as voltage sensitivity both are inversely proportional to the torsional constant. So lesser the value of the torsional constant, greater will be the value of the current or the voltage sensitivity. So in order to have a smallest value of the torsional constant, what we use the hairsprings made up of the special material which is called as the phosphor bronze wire. So this material has a smallest value of the torsional constant, due to which hairsprings when of this material are used in the galvanometer, they produce high value of the current sensitivity. Thank you.